Okay, perfect. So thanks, Vincenzo, for the introduction. I'm Greta Dolcetti from the University of Parma. Today I'm going to introduce to you to our latest work, which is speeding up static analysis with the split operator. This is a joint work with Vincenzo Arceri and Enea Zaffanella, both from University of Parma. So let's start with the presentation outline. First of all, we will see the standard approach, the filter operator on an abstract element. Then we will introduce our contribution, so the split operator, with a brief formalization, some examples, and the implementation in our adopted framework. And then we will continue with an experimental evaluation and conclude with the results and some future work we are thinking about. So filter is a common abstract operator. Of course, we are in the context of abstract interpretation, and it allows the modeling of the contour flow of a program in conditional branches. This operator is adopted by many tools such as CRUB, ICOS, LISA, and MOPSA, and goes by many names such as Assume, for example. As you can see, this operator works on an abstract element and a condition, a predicate. And what it does basically is that it refines the abstract element, and it basically produces the abstract element that meets the predicate, so the conditions. Let's see a simple example here on the left, and you can see that this is basically a simple if-then-else instruction that says if I less than 50, do this, else do that. We start with an abstract element A, and we want to filter the element. So we have to do two copies in order to filter then the element on the condition, so I less than 50, and on the negation of the condition, so I greater or equal than 50. Of course, we will produce the refined element for the condition and the refined element for the negation of the condition. As you can see, this approach is correct and is precise because at the end we have the two elements that we desire that are refined correctly, but may incur in some inefficiencies. For example, it introduces replicated works and overheads, of course, due to the copies and the two invocation of the filter operator. Of course, overheads introduced for simple domains, such as, for example, intervals, are neglectable, but for more computationally expensive domains, such as the polyhedra domain, they can be not neglectable, they can be important. So this is our new operator, the split operator. And basically, as you can see, it works on the two same elements of the filter operator. So it works on an abstract element and on a predicate. But this time, we are able to filter on both the predicate and its complement, its negation, at the same time. So it produces two abstract elements, the one which meets the condition and one that meets the negation of the condition. Of course, we had to implement this operator inside our domain of choice, and we implemented in the polyhedra library pp-lite for the abstract domain of polyhedra. And as I said before, the goal is to soothe some of the inefficiency that are introduced by the standard approach, so to achieve an efficiency improvement. Let's now analyze the same exact program as before. So if I less than 50, do this, else do that, but this time with the introduction of the split operator. As you can see, we start with an abstract element. It's the same as before, which is colored in blue. And then we have just one invocation of the split operator. And of course, this approach is both correct and precise because in the end, we have the same exact abstract domains that we obtained before. But this time, we have no replicated works, we have no copies, and hence we have introduced no overheads. And we are able to refine with just one single invocation of the split operator. So let's see some examples for the split operator itself on the polyhedral domain for linear constraint. So we have a polyhedron that it's defined on a bidimensional space, and this polyhedra is in the integer domain, so we are working in a discrete space. So let's suppose that we want to split the polyhedra on a disequality on this constraint that we are representing here with this dotted line that falls inside the polyhedra. So basically, the result for the split operator is this one. So we are able to produce the blue part of the polyhedra, the then part of the polyhedra that meets the condition, and the else part of the polyhedra that meets the negation of the condition. As you can see here, you may ask, why is there a gap between the two polyhedra? This is because we are working on a discrete domain, so the polyhedra cannot assume the values inside this. This is because of the discreteness of the integer domain. Of course, and as you can see, with a smart implementation of the split operator, as the one that we have in the PP-Lite library, we can refine much of the work and factorize much of the work that is done to compute the refined element for the condition and the negation of the condition. So we are working on the same polyhedra, but this time we are working on an equality, on a constraint that falls inside the polyhedra, which is represented by the dotted line. So as you can see, this time we obtain these two elements. The first one is the element for the then part of the polyhedra, and it's exactly the line that falls inside the polyhedra. As for the else part of the polyhedra, this time we would have two parts, one that falls on the lower side of the constraint, and one that falls on the upper side of the constraint, on the greater side of the constraint, we may say. And of course, as for the formalization of this operator, in the end, we should produce just two elements, one that meets the condition, one that meets the negation of the condition. So basically, we have to compute the p-else part of the polyhedra thanks to the join of the two parts that were produced that do not meet the condition. And basically, so we are able to exactly refine on the then condition, but we return the entire polyhedra on the else condition. As for another example, we have the same polyhedra, and this time we are able to split. We are splitting on a condition which is an equality that falls on the edge of the polyhedra. So this is a lucky example. The previous one was an unlucky example, we may say. And this time, with our implementation, we are able to basically capture the fact that there's no part of the polyhedra that falls on the greater side of the condition of the equality. So this time we don't have to compute any joins, and we are able to basically just refine on the else part of the polyhedra that falls on the lower part of the equality. So we are preciser in this case. So let's spend a few words about the tool in which we implemented and introduced the split operator. It's CLAM-CRAB, which are two modules of the C-ORN verification framework. CRAB is basically the C++ library for static analysis that offers abstract domains and fixed point engines, and it has its own intermediate representation, which is called CRAB-ER. It's kind of declarative, and it resembles the SSA form. As for CLAM, CLAM is the front end for CRAB. It basically translates C source code into LLVM bits code. It applies optimization and some preprocessing step, and then it translates them into CRAB-ER. So as for the introduction of the split operator inside this framework, we had to do two sets of changes. The first one were changes inside the abstract domain component. So, of course, we had to introduce a new method for the split operator in the abstract domains offered by CRAB, and because there was no operator for no method for the operator, and this method resolves to an ad hoc call to the function implemented in the PP-Lite library. So we also had to handle the unoptimized default implementation, so that if a domain asks for the split operator and is not implemented, we fall back on the standard implementation with the filter operator, which is always available for the domains offered by CRAB. So as for the second set of changes, we had to do some changes in the fixed point approximation engine. So we had to introduce a new abstract statement, which is the split statement, in CRAB-ER, so in the intermediate representation of CRAB. And then, we will see it in the next slide, we had to move where the invariants went stored. So we moved them on the edges instead of on the nodes. So here we can see an example for this simple function, which is basically a simple loop. And these that you can see are the actual CFG produced by CRAB in the CRAB-ER representation. So on the left, you can see the default CFG without the split operator. And on the right, you can see the CFG with the split statement. As you can see, we have basically 3 blocks to implement, to represent the conditional branches. And we had to introduce 2 basic blocks that are BB5 and BB6 in order to filter. So assume is basically the statement for the filter operator in CRAB-ER to filter on the condition and on the negation of the condition, with 2 copies that are basically used just to be able to filter on the whole element. And then we produce the condition that meets the abstract element that meets the condition, and the one that does not meet the condition, that meets the negation of the condition, we may say. On the other end, on the right, we can see that we have just the split operator, and this time we are able to refine with just one call, with just one statement on the condition and on its negation. One thing that you may notice, and also the CFG is smaller, but as you can see, we have invariants stored on the nodes as couples on the left for the invariants that hold before the basic block and after the execution of the basic block. But on the right, we have invariants that are stored on edges. This is because otherwise, at the end of this basic block, we would have produced a triple, because we would have produced 2 post invariants, one for the then condition and one for the else condition. So we simply move them on the edges. And at the end of the analysis, we introduce the finalization phase, which, thanks to join operation, computes the invariants as CRAB expects, so basically as couples. So some notes about the split statement in CRAB. So CRAB offers limited support for floating point operation, so tests for floating point are ignored, and also for unsigned variables. And our prototype also ignores the select statement, which basically models implicit conditional branches. So as for the experimental evaluation, we evaluated our prototype on the PP-Lite abstract polyhedra domain and the Enea domain without the split operator, and then on the PP-Lite domain with the split operator. We tested on 2 sets of benchmarks. The first one is composed of 39 files, which are distributed with the Pagai analyzer and are usually adopted for the worst-case execution time analysis. And the second one is composed of 7 files that are Linux driver distributed with the SVComp benchmark. And as for the CRAB configuration, we adopted the default configuration. And so we had done just numerical analysis in invariance analysis. And in this configuration, switch statements are lowered. And what we added is that we had a systematic inlining of function calls in our benchmarks. So for the experimental evaluation itself, we evaluated then on times and then on memories. And for the times, as you can see in this table, we have the tests followed by the times for the PP-Lite domain without the split operator, with Enea domain without the split operator, and for the PP-Lite domain with the split operator. In the last column, we can see the ratio between the PP-Lite domain without the split operator and the one with the split operator. So we compare the times with Enea, which is one adopted library for abstract interpretation. And as we can see, on the last column, we have usually significant speedups, and with some peaks in which we are up to 4 times faster as with respect to the implementation without the split operator. One thing that I want to mention, and is important to mention, is that we are able to achieve these significant speedups without any precision loss at all. So this is a nice thing to have. And as you may notice, we have some few slowdowns, as you can see here, and these are due to the finalization phase. So as for the memory, this was a nice side effect because we measured the peak memory usage in a megabyte for each test in the no-split variant and with the split operator. And as you can see, we usually use less memory. And in the same test that was 4 times faster, we use 27 times less memory respect to the implementation without the split operator. And as for the nodes of the CFG in CRAB ER, as you saw before, the CFG tends to shrink because we use less blocks and less assumed statement. So we are steadily using less memory. We have a CFG that has steadily less nodes inside them. So basically concluding, our prototypal implementation was able to achieve non-trivial memory and time improvements. And the most regrettable thing is that we achieved no precision losses at all. We were able to prove this thanks to a tool implemented in CRAB CLAM, which is called CLAMDIF, which basically does the comparison between the invariants computed by 2 analyses in both a syntactic and semantic way. And as for future works, we are willing to introduce the split operator for other abstract domains. And of course, the more expensive domains are a better candidate because they are willing to introduce a greater overheads in the copy in the CFG. And one other thing that we plan to do is to extend this operator to other tools. With that, I conclude my presentation, and thanks for your attention.
Thank you. Any question? Yeah, I have a question about the alternative CFG representation. So that seems to be good since it leads to smaller CFGs and you save memory and everything. Are there any drawbacks, or is this just should I just use the CFG representation no matter if I have a split operator or what or not? Is it just always better?
Actually, I don't think so, because CRABs for other analysis expects the invariants as a couples. So in the end, you have to do the finalization phase that takes time because it has to compute many joins. So basically, moving just invariants without the introduction of the split operator is not as profitable as using the split operator.
Yeah. So I have a question on the left-hand side, the assume statement. So you have the less or
Sorry.
oh, this was the
Sorry.
you have I0 less or equal to 49 on the left-hand side,
Yeah.
and less than or equal to minus 50 on the right-hand side. Why is it minus 50?
This is the actual representation for CRAB, and you may not see because it's in small, but it's minus I less or equal than minus 50 is just how CRAB represent the condition, so it's negated. But if you just convert it, it's high greater or equal than 50. There's a minus here.
It's minus. Okay,
yeah,
okay.
Yeah, it's minus.
Okay. Okay.
Yeah, there's a minus here
okay.
and here. So
Yeah.
you have to just convert it to the positive.
Okay.
So
Yes, and it makes sense because
Okay.
I was thinking it was wrong in my head. So yeah.
Thank you.
Any other question?
So from the experimental results table, do you have any insight in what cases you get, better rush? I don't know, on the structure of the program, maybe, I don't know, while loops or there's some specific type of condition helps you to improve the performance.
At the moment, we did not analyze the structure of the program, so we will maybe doing that in the future. And we just basically, there's a hidden slide here. Okay. I don't know if, that's 1 second. Let me just hit them. Okay. Okay, so here you can see that the thing that we done, it's basically the same as the graph in the next slide. We just counted the number of the split operator in the CRUB CFG for any of the program in the benchmark. And yeah. And one other thing that, of course, I forgot to mention, is that we report just the program that exceeded 1 second in the analysis, because the worst case execution time benchmark was made of smaller files. So even with inlining, they were a bit small. So as expected, you have basically major speedups on the bigger benchmarks of the Linux drivers.
Okay, yeah.
Hi, so you mentioned you don't support the select operator. Do you want to, is there a specific challenge with it, or?
No, it was not supported at the moment of the publication of the paper because of time issues, but we are just developing it now.
Thanks.
Okay. Let's thank again the speaker. Thank you.